Okay, good. Yeah. So stop me whenever you feel like. So the title is monotonicity testing and boolean isoperimetric type theorems. This is joint work with Muli Safra and his student Dor Minzer. And the paper is available on ECCC if you want to take a look. So we'll be looking at boolean functions on the n-dimensional boolean hypercube. A function is called monotone if this is the definition, right, where x less or equal to y means every bit of y is greater or equal to every bit of x. Right, then f of x is less or equal to f of y. Or another way to think about it is if I change a coordinate from input coordinate from 0 to 1, the value of the function can only change from 0 to 1. It cannot go from 1 to 0. So here is kind of a standard pictorial representation of what a monotone function is. If you think of this as the Boolean hypercube with 0 to the n, the bottommost input, and 1 to the n as the topmost input, then the values of the inputs at which the function is 1, it's some kind of some upper subset of this picture, right? And many of the standard functions are monotone. The dictatorship function, the standard majority function, and equivalent characterization of monotone functions is these are functions which are computed by circuits that only use AND and OR gates, right? You don't use NOT gates. And here we are interested in a problem of testing whether a given function is monotone. And this is in the standard setting of property testing, which you might be familiar with. So you are given query access to a function, and you are allowed to query the value of the function at any input of your choice. And you want to make as few queries as possible. And in a randomized fashion. You can choose your queries in a randomized fashion. And then your tester, you want a completeness property and a soundness property. Completeness property, it says that if the function is indeed monotone, then you ought to accept with probability 1. The soundness property says that if your function is far from being monotone, and the far is in terms of Hamming distance. So think of, at least for now, epsilon as say 1%, meaning the function has the property that if you want to make it into a monotone function, you got to change at least 1% of its entries, right? So it's far from being monotone. In that case, your tester has to somehow detect this fact that the function is far from monotone. And this, let's say, that the tester accepts with probability at most 1/2. So this is the this is the kind of tester that we want. So for now, I will give an example of a generic tester, okay? And think of the tester as this generic tester. So I will say about a little bit more about non-generic testers. So here is something very generic that you can do. More or less, I think this is the obvious thing you would do in the first shot. So let me fix some distance parameter, tau. You could even think of tau as 1 for now. And you pick, so this is the hypercube, right, the same pictorial representation. You can pick two inputs, x and y, such that y is distance tau above x, meaning you can change tau of the 0 coordinates of x into 1, right? And you look at the values of the function at x and at y, and if you detect that it's a violation to monotonicity, then your tester rejects, right? So what a violation means is the value of the function at point x equals 1, but the value at y is 0, right? So that would be a violation of monotonicity, and then your tester would reject. So this is what I call a generic tester. Okay. Now 2 comments. So 2 comments. Firstly, the tau itself you could have chosen from some distribution to begin with. So that's one thing. And secondly, for this tester, you can either focus on, of course, the completeness holds, right? If it's a monotone function, you are going to accept with probability 1. For the soundness property, you can either think of just this tester and look at the probability of rejection, okay? And in fact, we will see that if you just fix tau to be 1, then this tester has a rejection probability which is epsilon over n, where epsilon of f will denote distance of the function, distance to monotonicity of the function. Okay. In particular, if the function is epsilon far from monotone, the rejection probability is at least epsilon over n. And maybe this is good enough for you. If you care about getting constant rejection probability, you would just repeat this enough times, right? So in this case, you would repeat n over epsilon times. And throughout the talk, I'm going to ignore constants everywhere, just for the sake of clarity. Okay, and this tester, this was proposed. Also, the problem was proposed, and the tester was analyzed in a paper of Goldreich, Goldwasser, Lehmann, Ron, and Samodensky in 97, 98. Okay. And after this paper, there was much progress in many different directions. For example, you could consider, instead of Boolean hypercube, you could consider general posets. You could consider related problems such as estimating the distance to monotonicity. This is related to routing or paths and routing on the hypercube. So there were many, many papers. However, for this basic problem, there was no improvement beyond this until a recent paper of Chakrabarty and Sheshadri. So I will so I think I can just erase this. So they and it's more important to improve the dependence on n as opposed to the dependence on epsilon. In fact, the property testing people, they are going to agree with this. It's not controversial. In any case, in the end, we will see a tester which is optimal in both the parameters. So this is the GGLRS result, and the Chakrabarty and Sheshadri, and this result was improved slightly by doing like one more trick. So this is a paper of Chen, Servideo, and Tan. So in their setting, tau itself is chosen at random. So you could choose tau to be powers uniformly from powers of 2s up to roughly root n. Okay. So you don't want to exceed root n because then the inputs x and y, you want them to be roughly in the middle, right? Because those are the typical average inputs. So you don't want to go too further. So you pick tau uniformly from the powers of 2s, and then the tester is the same. And they showed that the rejection probability is at least, again, I mean, ignore the dependence on epsilon, but n to the 5/6. So the CS paper, they got n to the 7/8, and then it was improved to 5/6. And the number of queries is just the inverse of this. So that's the Chakrabarty Sheshadri paper, and we will give the optimal one, which would be epsilon squared over square root n. But let me start by telling what Chakrabarty and Sheshadri did. The tester is the same, okay, right? It's really the analysis which is relevant. Yeah, I will say the lower bounds, and you will see that epsilon squared over root n is the optimal in many, many respects. I will say everything. Just wait. Okay. Or maybe I could state the results first, and then we could do it the other way around. So what we do, this paper is the same thing. The probability of rejection is epsilon squared over root n. I'm ignoring constant factors and even log factors. So let's ignore. Yeah, the tau distribution is the same. So for lower bounds, so there is some subtlety, but more or less it can be argued that this is optimal in both the parameters epsilon and n. So for the lower bounds, a paper of Fisher, Lehmann, Newman, Rakshadnikova, Rubinfeld, Samodensky in 2002, they already showed root n lower bound. If you ignore the dependence on n, so if you think of epsilon as constant, sorry, if you ignore the dependence on epsilon. And this holds even for general testers in the sense that this you can call as a pair tester, right? You look at a pair, but you could be more general. Maybe you pick the bottom input x and then 3 inputs y1, y2, y3 which are above that. You could do something, right, something general. But this lower bound holds even for general testers. Okay? So in a recent paper, so this is the Chen, Anindya Day, Servideo and Tan. They prove again n to the essentially square root of n, and this holds even for general testers and even with imperfect completeness, right? You could allow imperfect completeness that even if the function is monotone, maybe the tester is allowed to reject with some small probability. So this holds even for that. In our paper, well, I guess so it's clear that root n is the right answer. So in our paper, we also show a rather simple lower bound and show that if you insist on dependence on root n, then you need the dependence on epsilon has to be epsilon squared. Moreover, it's very easy to observe that in principle you could say, I'm going to design a tester which has the dependence n to the alpha epsilon to the beta. Okay, why not? But you can easily check that no matter what alpha beta you choose, we show that alpha plus beta over 2, this at least needs to be 3 over 2, that we do. And if so, then actually there is no point in having n to the alpha epsilon to the beta tester. You might as well consider either n over epsilon, which is the Goldreich et al., or root n over epsilon squared, which is what we have. And then one of the two will always be better than this. It's a simple, some sort of interpolation. So those are the lower bounds. So whatever we have is basically optimal. So I will, we'll start by what Chakrabarty and Seshadri did. So they started with this really observation. So now I have to write 9 theorems and tell you how they are related, right? But as you will see, it's going to be relatively quite clean. So look at the Goldreich et al. Tester, right? It just picks an edge of the hypercube and checks if the edge is a violating edge, right? And the fact that the rejection probability is epsilon of f over n is just saying that if the distance to monotonicity is epsilon of f, then there must be lots of violating edges. Okay, that's all there is. So their result is just an inequality, right? So this is the Goldreich et al. Inequality. So let me write it down. IF minus is at least epsilon of f. Okay. So where IF minus, this is going to be this is going to denote the so-called total negative influence of the function, right? So this is the number of violating edges divided by 2 to the n. And in fact, it will be useful to look at a graph. Maybe I should draw the graph first. So this is simply the graph of all violating edges. So something like this. And edge is violating if the inputs, so these are points of the hypercube, right? And edge is violating if x is less or equal to y, the value of the function at x is 1, and the value of the function at y is 0. Right? And of course, xy is the edge of the hypercube, meaning x and y differ on only 1 bit. So given any function, you can look at this graph. These are graph of violating edges. Okay, and let's give it a name. Let's call it gf minus. Call these vertices v minus, the vertices on this side w minus, and the edges as e minus. Okay. Good. And then the Goldreich et al. Result is just right. So this is the Goldreich et al., which simply says that IF minus is at least epsilon of f. Because on this side the value of the function is 1, and on this side the value of the function is 0. So right, and then the edges are the violating edges. So that's the Goldreich et al. Result. And what Chakrabarty and Seshadri, well, I mean, what they proposed is whatever this inequality is, we want to think of it as analog of a standard boolean isoperimetric inequality. So here is a standard Boolean isoperimetric inequality that the total influence is at least equal to the variance of the function. So variance is simply using a simple dictionary. You just replace the total influence by the total negative influence, which looks okay, but then you replace the variance by distance to monotonicity, right? Which is not clear why you should be doing this, but let's do it. And then it kind of helps to have the corresponding graph here, which let's call it G sub f, and this is a standard graph of all these sensitive edges, meaning all the edges at whose endpoints the value of the function differs. Right? So this is a graph where these are vertices where the value of the function is 1. On this side, the value of the function is 0, right? And then these are all the edges of the hypercube. So this is clearly a subgraph of this, right? The difference is that here, so this graph only contains those edges for which x is less or equal to y. So, right, here you allow, in some sense, if you take the hypercube and direct all the edges in increasing direction, right, then this graph contains only the forward edges. Yeah. So this has only the forward edges, and this will have both forward and so-called backward edges. Does this make sense? But if you just want to think of these as standard graphs, this is really a subgraph of this. Okay, it only contains some of the edges, right? And then right, the total influence would be simply the total number of edges, and so on. So so I wrote the definitions of total influence and everything else. Okay, so this was Chakrabarty and Sheshadri proposal. Somehow we want to think of this as a directed graph, and these inequality as a directed analog of the standard undirected inequality. Okay, and now once you have this proposal, right, now you can begin the game. Why not take a theorem which is a stronger theorem than this, or maybe more general theorem than this, then prove a directed analog of it, and then hope that it helps to analyze the monotonicity tester. Okay, and this is what they did. So they looked at a theorem of Margulis from 74, which states that for any function, the total influence multiplied by the size of the vertex boundary is at least the square of the variance. Again, I'm ignoring constant factors. So what is vertex boundary? Vertex boundary is simply, if you look at that picture, is the size of the set V divided by 2 the n. So these are all the vertices on the one side of the function which have at least one sensitive edge. Okay, right. So if you, the picture was lost, but pictorially, if this is the boundary, then these are the vertices on this boundary, on that surface. Right, and they show that you cannot have the total influence as well as the vertex boundary. The total influence is really the edge boundary, size of the edge boundary. So you cannot have edge boundary and vertex boundary simultaneously small. Right, and maybe it's instructive to check this. If you take a dictatorship function, the variance is constant, total influence is 1, and the vertex boundary is also 1, because for a dictatorship function you will split the set into 2 parts, and everything on the left side or the right side, whichever is the case, counts as a vertex boundary. So the vertex boundary is also constant. So constant times multiplied constant is at least a constant. On the other hand, you can take majority function, and for the majority function, the vertex boundary is 1 over root n, because right, it will be the middle layer, exactly middle layer. So that's 1 over root n. But on the other hand, the total influence happens to be root n, right, and then the product is still a constant. So that's the Margulis inequality. No. In this case, whatever is written on the left-hand side, it's for any function. Okay. So that's the Margulis theorem, and the Chakrabarty and Seshadri, they managed to prove the analog of the Margulis, right? Okay, exactly. And of course, the negative vertex boundary will be defined similarly. The size of this V minus divided by 2 then. Okay. And actually, to apply this to the monotonicity testing problem, they actually need a statement which is even stronger than this, which let me write it anyways, though we won't really need it. So this is Chakrabarty and Seshadri. So here, if you interpret this statement as saying somehow the vertex boundary is large, okay. So what this actually gives you is that not only that then this set is large, right? In fact, there is a large perfect matching from this set to this set, a perfect matching of violated edges. Okay. So it says something stronger, but let's not kind of dwell on it. And well, let's not dwell on it, but it's very easy to show that actually this is more general theorem than this. So this implies this. Similarly, this implies this, and this implies this. Okay, so this is what Chakrabarty and Seshadri did. And yeah, so when we started looking at this problem, we were actually lucky that the Margulis paper appears in Russian, because if you start searching for it, well, it's Russian, right? So you're not going to read it. And you will find that actually the proof of Margulis which is available most immediately is actually proof by Talagrand of an inequality which is even more general. Okay, so yeah, so one is naturally led to the result of Talagrand, which says the following. I will write down the statement first. So expected value of square roots of whatever this quantity is, just think of this as degree in this graph. So expected value of square root of degrees is at least equal to the variance. So what is this quantity if of x? It's simply the degree in this graph. So suppose I have input x, then you look at the degree, and this degree is if of x. Yeah, the distribution is uniform on the, so if you want, one could write it, this is, and somehow in a somewhat asymmetric manner, it's defined to be 0 if f of x is 0. So it's defined to be only degrees on the v side, and then the degree if f of x is 1. So okay, so that's the Talagrand inequality. And I said this implies the Margulis one. That's just by Cauchy-Schwarz, so let's not do it. But it's very easy to see that the Talagrand is stronger than the standard folklore one, because the total influence would be simply, you would be taking expected value of the degrees, just the total number of edges. And now you are taking expected value of the square root of the degrees, which could in principle be much lower, right? But it's still lower bounded by the same quantity, which is the variance. Okay, so it's clearly a stronger result. Which one? Is that a quantity bigger than 1 or less? The left-hand side? No, these are the degrees, right? So the degrees can be, okay. Yeah, so this if of x, it can be any, it's an integer from 0 through n.
Normally it's specified as a property.
Yeah, but at least, yeah. So that's the Talagrand. Now it's kind of natural to ask whether we can show analog of Talagrand, right, on this side, and that's what we do. So we show, so that's this paper. So this is the analog of Talagrand, expected value over x, square root if minus x is at least distance to monotonicity, and this is the same. 0 if f of x is 0, and then the degree of x, the minus degree of x if f of x is 1. So these would be degrees in this graph, right? So this is what is. Okay? Yeah.
How many of these isometric inequalities are very specific to the hypercube, like
Yeah, I didn't really investigate, but people have certainly studied these things with respect to the product measure on the hypercube. So I'm quite sure they also studied for different domains. So that's kind of one of the main results. And then somehow even this is not actually good enough for us if we want to apply it to the monotonicity testing problem. So we really we really need a robust version of this. So I won't really kind of spend time on defining this robust version, and we also need a robust version of this as some sort of intermediate result. So I'm not going to say what it is, but I will maybe quickly just say a sentence. So it's kind of clear that somehow you are looking at the degrees only from the v side, right? Which looks a bit arbitrary, right? And you could try to somehow symmetrize the role of the v side and the w side. So one way to do this is the edges you are allowed to color by two colors, either red or blue, arbitrarily, okay? And then you look at this quantity, you are counting the square root of the degrees, but from the v side you will only look at the red degree, and from the w side you look only at the blue degree, okay? And then take the whole sum, okay? And then that's at least epsilon, no matter what your red blue coloring is. In particular, if you colored all the edges red, you are just going to get this. If you colored all the edges blue, you will get the same statement if you started counting the degrees from the other side, which ought to be the case, right? Why should it matter which side you count the degrees on? And then this is even more general. No matter what coloring you do, you get it. Okay, so that's that is the robust version. Okay, and then it turns out the robust version is good enough for to analyze the monotonicity analysis. It's already good. It's also good enough if you want to derive this bit stronger theorem of Chakrabarty-Seshadri. Okay, and that's all there is. And I'm kind of cheating a little bit. In all our results, we lose a log factor. So there is really log n divided by log 1 over epsilon, which I'm ignoring. So one quick comment. So this analogy, right, between the undirected case and the directed case, I would really think of this as just informal analogy. I mean, there is no fundamental reason why these ought to be true. They somehow just happen to be true. Okay. And the proofs on this side, they are just completely different and much more complicated than the proofs on this side. Okay. Though I mean, at the end of the day, we did notice that these theorems do imply the corresponding theorems. So there are all the horizontal arrows in between. I mean, it's not obvious, but it's small argument. Okay, so that's kind of the whole picture of all these theorems. And well, there is a connection, but it's only in one direction. And then, in some sense, somehow the connection doesn't necessarily tell why this has to be true, right? It's okay. So in the remaining time, what I will do is I will try to give some idea of the proof of this inequality, and maybe just say maybe in the beginning I will say a few words about how it implies the monotonicity testing analysis. So that the analysis of the tester. So the tester is the same, right? So it's really the matter of the analysis. So we start with this theorem, this directed analog of Talagrand. So what this, well, clearly, right? The inequality gives me some control over, right, in this graph, in this negative edges graph, how many edges there are, how their degrees are distributed, and so on, right? And using this control that we have on the right, the number of vertices and their degrees, one can conclude that graph, right, the graph of negative edges, it has a appropriate subgraph. Okay, an appropriate meaning with the following properties. This is B minus. So it has a subgraph. So there is a subset of vertices A on this side, subset of vertices B on this side, and the subgraph is between A and B, such that all the degrees on the A side, they are exactly D. Okay. Now, what does this inequality tell us? It actually tells us the following, that this, there must be such set A such that size of A divided by 2 to the n times root D is at least epsilon of f. So why is this? Because you are really just taking average over square root of the degrees, right? And that's at least epsilon of f. Now the degrees, you could bucket them into degrees which are roughly 1, roughly 2, roughly 4, roughly 8, and so on. And out of these log n buckets, you can take the bucket which contributes most, right? So it's going to contribute at least epsilon f4 over log n. So you take the most popular bucket, and then take the vertices of that degree, right? And then this is exactly this, right? The size of A, relative size of A multiplied by root degree, right? So so there is a subgraph like this, where all vertices on the A side have degree D, and you have this inequality. Now, what this robust version allows us to conclude is an additional property, that on the other side, that is the degrees on the B side, they are at most, let's say, 2 times D. So this is what one buys with this robust version. And then once you have a subgraph with this property, right, degrees on one side are D, the other side is at most 2D, something like this, then this implies the analysis of the monotonicity tester, which I'm not going to present. It's a new analysis, different than the previous analysis of Chakrabarti Sheshadri. It also has few more, in fact, quite a few more additional ingredients, but I'm going to skip it and focus on proving the inequality.
But this cannot happen, or you assume you have lots of edges and therefore the distance must be.
Sorry, say it again.
It's just maybe it's just semantic, because there's a tautology. You can assume that distance to monotonicity is small and prove there is no such structure, or go the other way to prove that you have this structure.
Yeah, so no, so you actually raise, in fact, a very good point, in the sense that it's really the direction of the argument, right? So okay, so in the prior work, the argument is actually quite clear, the direction. You assume that the left hand side of whatever your inequality is small, and then you give a sequence of transformations which changes the function into a monotone function, and then you worry about what's the fraction of the values of the function I changed. Okay, so in that sense, you are assuming that this is upper bounded and concluding that therefore this is upper bounded. In what we do, it's not so clear. It's all just jumble of things, and there is no somehow such a clean answer. Right? There is definitely a sequence of transformations, but then it's a sequence of transformations applied to some random restrictions of the function. Yeah, it's not so clear. Yeah, but no, but that's a very good valid point. Yeah, so we want to show that Now, so many isoperimetric inequalities. Yeah, if you are familiar with some of them, you would know that these are proved by what is known as symmetrization argument. So what it does is it looks at the inequality, and then whatever your function f that you start with, there is a sequence of operations on this function, which in some sense makes the inequality even tighter and even tighter, right? And in the end, you get a function which is hopefully simple function for which you know the inequality, right? And then you are done. Okay. So one could attempt something similar. So in particular, we will have a transformation or an operator on a function such that this left-hand side, it can only go down, okay? And the right-hand side, one would hope that it stays roughly the same, okay? And then the final function, it's simple enough that for the final function, we know the inequality. Okay, so that's kind of at least the first thing one would try. So let's write this down. And this transformation, we call it the split operator. Maybe I will say what it is towards the end. So given a function f, the operator, this has nothing to do with gradient. It's just somehow notation that looked convenient. So right, you construct a new function g with the following properties, that the left hand side, it can only go down. So this is less or equal to the same thing for g. So the left hand side can only go down. So the Talagrand objective, this can only decrease. Whatever inequality you are interested in proving, it is true for g. So this is at least epsilon of g, the distance to monotonicity of g, right? So the inequality holds for g, in the sense that g is somehow a simple enough function that you can do it. In fact, it just follows by using the original Talagrand. And then one would, so these two steps are correct. And then maybe one would hope that this is at least comparable to the distance to monotonicity of the function f. Okay? But this is false in general, and one needs to get around this. Okay? So I will say what the split operator is maybe towards the end, but at least here somehow there is another operator called switch operator, which is kind of one needs to introduce first. And then I will say how the split operator, at least morally speaking, relates to the switch operator. Okay? And the switch operator, this was proposed by the Goldreich et al. In their first paper. Hopefully we can fix this. Yeah, so recall that the Goldreich et al. Paper, what they showed is that the total negative influence is at least the distance to monotonicity of a function. So this they prove using the so-called switch operator, which works as follows. So start with an original function. So this is the function f, and from this, and let's say the vertical direction denotes the coordinate number 1. This is the first coordinate, so that this is a plane with the coordinate equals 0. This is the plane with coordinate equals 1. Now suppose, and look at the edges along that coordinate, and suppose here the value of the function is 1, and here the value of the function is 0. Now clearly that's a violation of monotonicity, right? And if you want to make the function monotone in that coordinate, you will have to fix these violations. And one thing you could do is simply swap the two values, right? Push the 0 here and 1 here, the values. Okay? And that's what the switch is. You fix a coordinate, look at the edges along that coordinate, and do the swap. Yeah, simultaneously for all the edges. Yes, yes. Yeah. Yes. So yes, yes. Yes. Yeah, yeah. Yes. Yes. Right. So you just make do the swap but for all edges, right, simultaneously. You fix a direction, right? And I'm only going to making it monotone in that direction. Okay, forget other coordinates for now. Okay, so let's call this function f, and then this operator is s for switch, and s1, meaning it's s on the first coordinate, right? And there is actually a very compact way of writing what this operator does. You look at every edge. The edge is thought of as being vertically, and then if the value of the function at the endpoints is a and b, then the value of the function at the the new function at the same endpoints is min of ab and max of ab. Just compact way of writing it, meaning if the edge is already monotone, do nothing. If it's monotone, then switch it. So yeah, so this is what Goldreich et al. Proposed, and then what they showed is the following. So I start with the function f. I applied the switch operator on the first coordinate. So now the function became monotone on the first coordinate, right? Now suppose I apply the operator on the second coordinate. So clearly, right, I applied s2. So the function did become monotone in the second coordinate. Okay, but what they observed is that it doesn't ruin what was done before, in the sense that if the function already became monotone on the first coordinate, applying s2 does not kill it. So it still remains monotone on the first coordinate. Yeah, you somehow seem to be thinking about it. I would recommend not think about it. It's going to somehow, it's a case analysis, right? So it's well known. Well, perhaps it was known, but at least I know this from this paper.
It's the same operator used to prove the underexpression.
Oh, okay, okay.
It's also the same operator used to prove, let's say, the sour lemon.
Yeah.
It's exactly the same. You monotonize.
You monotonize. Oh, okay, okay, at a time.
It's the same.
Okay, okay. So then maybe this fact was known before, that if you apply the coordinates 1 through n, right, let's say in that order, then the final function is monotone. So this, right? So this is what, and then you need to make some more observations, and right, which are quite nice, and that leads to this inequality. Now, here is something nice about, right, you moved from original function to this final function, which is monotone, right? So now you can ask, what's the fraction of entries of the function that I changed? Okay, so the Hamming distance between the function f and this final function. Okay. So clearly, right, I made my function monotone, so it must be at least the distance to monotonicity of the function. Okay, so this is obvious, and then it's a quite remarkable observation that this is at most 2 times the epsilon of f, meaning, in fact, this is basically the most efficient way of turning a function into a monotone function. Okay. No, again, it's not obvious at all, but it needs like maybe half a page of proof, and in fact, we thought that this was a new observation, and we were quite happy. And in fact, we even asked many of the researchers, and they didn't know this either. But in the end, it turned out this was known in a paper of Fatal and Ron. But this one 2010, which is, I was really surprised. Somehow this fact wasn't known before until 2010. Yeah, I don't know what the reason is. Maybe people somehow didn't care so much, or maybe it's something. Yeah, maybe it's something unexpected. So you wouldn't, in some sense, attempt to prove it. But once you attempt to prove it, it's easy. Right? But in any case, it doesn't matter. It's quite simple and useful. So that's the switch operator. And now let's introduce a notation. So suppose pi is a subset of coordinates 1 through n, and it's best to think of this as simply a prefix of coordinates up to k coordinates. So if it's a set of size k, it's thought of as coordinates 1 through k. And then let s sub pi f denote the function f with the switch operator applied on coordinates in pi, meaning up 1 through k. But k could be something less than n, say n over 2, in which case you would apply the operator on the switches only on half the coordinates. So f with switch applied to coordinates in pi. So that's the notation. And now let's go back to our proof strategy, right? We wanted to prove this inequality. So we'll start out by saying square root of this. I haven't yet defined what this switch operator is and how to construct this function g, but I will at least say what it is, at least morally speaking. The split, sorry, split. Yeah. And this needs, this will hold. It will also hold that the inequality holds for the function g, and then in fact this will morally, at least this is just an equality, that g, morally speaking at least, is simply f with the switch applied to half of the coordinates, say coordinates 1 up to n over 2. You don't go all the way till the end, right? You stop in the middle. Right? So g, morally speaking, is simply s pi f with size of pi equals n over 2. Okay. Right. So this is So this is simply distance to monotonicity of the function s pi f. So now now let's look a bit more closely at how the function changes as you keep applying these switch operators, one coordinate at a time. So you start with your original function, f. Maybe you applied the switch on the first coordinate, right? And maybe the function moved here. Maybe you applied switch on the second coordinate, maybe it moved here, and so on and so forth, right? So in the end, you got to the function f with switch s1 up to sn, right? That became monotone. Yeah, so the order matters, and that complicates the order matters. That complicates things, right? Yeah, but then in the end, there is going to be averaging over all random orders and everything, which I'm going to skip. And this function s pi f with size of pi equals n over 2, it will be somewhere in the middle, right? Okay. Now, the lower bound that we have is distance to monotonicity of this function. Okay. Now, since this final function is monotone, the distance to monotonicity, again, at least morally speaking, is simply this distance. right? So this is simply at least morally the Hamming distance between S pi f with size of pi equals n over 2 and S pi f size of pi equals n, meaning if you went all the way up to n, okay? Which by triangle inequality, this shaded distance, I could start measuring all the distances from the original function, and then it will be this distance minus this distance, or at least. Right? So it's at least distance from f to the last point, S pi f with, okay? Yeah, so this is what we get. Whatever, this is the quantity that we want lower bound on, and we do get lower bound of this nature. Okay? Now this lower bound actually might not give you anything because it's actually possible that if you apply all n switches, the function did become monotone, but maybe the function becomes monotone even after doing n over 2 switches, meaning this gets really close to this, right? In which case you would get nothing. But once you stare at it, you would kind of you would be led to the guess that one ought to get inequalities of this nature. So this is in some sense giving a difference between n versus n over 2, okay? And it suggests that one could get such an inequality for a difference between n over 2 and n over 4, and n over 4 and n over 8, so on and so forth, okay? And I will get all these inequalities, log n of them, because, right, and then it would be a telescoping sum. I would sum it up, and that's it, okay? In the sense that even though this distance could be, it could be very small, maybe, right, this distance would have to be large either between n over 2 and n, or between n over 4 and n over 2, or between n over 8 and n over 4. Somewhere this distance has to be large, okay? And that's basically it, right? So so what we actually get is whatever this quantity we are trying to lower bound is at least that, and distances are always measured from the original function. So distance of the function S pi f, size of pi is n. Let's even say n over 2 to the j minus distance from f to S pi f, size of pi is n over half of that, n over 2 to the j plus 1. For any value of j, we will get it. And now, right, you get this. Well, it needs more work. You have to look at now random restrictions of the functions rather than the function itself. Yeah, but you get this, and then you get log n such inequalities. You could add them up, and you would get log n times whatever the lower bound that you want is at least the first term minus the last term. The first term is f, distance of f from the monotone function, which is all the switches applied, minus the last term would be distance of f from itself, because I don't apply any switch whatsoever. So this is 0, and this is at least epsilon of f, right, because this function is monotone, right? And then you get whatever you want is at least epsilon of f, but you lose a log factor. And that's sorry? Yeah. So this I use somewhere in this moral argument, switching between yeah. No, but this is at least, this is easy. But the somewhat more trickier direction I used in the middle. Okay, good, right? So because whatever my split operator, which I haven't yet defined, really, it's morally speaking, it behaves as if you apply the switches on random set of half of the coordinates, right? So. Yeah, yeah. At least the way it is defined, it does half. Yeah. So I guess I'm kind of out of time. If there are like maybe 5 to 7 more minutes, I could at least define what this split operator is. And actually, it's quite incredible how many properties it has, in the sense that it has to have every property to make every step go through, right? Which is quite. So the switch operator I described, right? So it's you should think of it as an operator applied on one bit, right, to an edge, which maps an edge with values, the function values a and b, to function values min of ab and max of ab, right? And this is operator defined on one coordinate, and of course, right, you can apply it on an entire function by applying it on the one coordinate for every setting of the remaining coordinates, right? So, right, this is clear that this completely defines what the operator is, even on multi-dimensional functions. Yeah, yeah, yeah. We wanted to call it in the Goldreich-Kettel paper. We wanted to call it swap, but they called it switch, so we stuck to switch.
No, I'm surprised because some of them look a bit
Okay, so that's the switch or the shift, and here is the split. The split operator actually it changes a function of 1 bit into a function of 2 bits. Okay, so it's a bit different. Now it's a function of 2 bits, right? So there is a quadrilateral, and you will have to define values of the function at the 4 points of the quadrilateral. So here it's at the bottom and topmost points is the same, a and b, and on the midpoints it's min and max. So the inputs are really like this. This input is 0, 0. This input is 1, 1. This input is 0, 1, and this input is 1, 0. If you apply on one coordinate, then that coordinate splits into 2 coordinates. If you apply sequentially on all n coordinates, then in the end you will get a function of twice the coordinates. Okay, so that's what the split is. Now, 2 properties. Firstly, in some sense, if you ignore the midpoints of the quadrilateral, the function is the same, a b, right? It stays the same. So it's like do nothing with probability 1/2, and if you look at the middle layer, you get min ab, max ab, and somehow if you orient yourself going in this direction, it's exactly applying the switch operator. So it's like applying the switch operator with probability 1/2. Okay. So yeah, so if you applied the split on all n coordinates 1 by 1, it up yeah.
When you apply to one coordinate,
Mm-hmm.
you do it for all the edges.
Yeah, yes, yes. Yeah.
So it's not just quite like probability half, unless you do it simultaneously. So this bit flip, if you look at this direction or this direction, it's coordinated. You want one bit flip from all these.
Maybe in the end I will say one concrete statement. Okay, that will in some sense will clarify what I mean by this operator is morally speaking same as the switch operator applied to half the coordinates. Okay. So I'll make a precise statement.
I understand. I'm just asking. Okay. When you do the split operator and you view it in this direction, the horizontal direction, in all of them, the ordering became consistent.
The order became
Between the minimum and the maximum. So you monotonize, like in the original switch operator, you monotonize all the edges.
yes. Yeah, yes,
So
yes.
this bit, what I'm saying, this bit split is for the coordinate rather than for particular
Yes, yes, for the coordinate. Yeah, exactly. Yes, yes. Yeah, you're right. Yeah. Okay. Right. So at least from this picture, one could believe that, right? So G is at least the split is really morally it behaves as if with probability half you do nothing, and with probability half you do the switch. But I will make a more precise statement later. And then yeah, and then the real kind of key is the following, that if you look into this quadrilateral now, it's a function of two coordinates, right? And the coordinates are really these directions. Okay. In this direction, actually this function is monotone, because right, in this direction min of AB is less or equal to B, and A is less or equal to max of AB. So in this direction it is monotone. In this direction it is reverse of monotone, or you could call it anti-monotone, because min of AB is less or equal to A and B is less or equal to max of AB. So in this direction it is anti-monotone. So what this operator does is, originally this coordinate, it could be in some sense mixed coordinate, in the sense that depending on the setting of all the other input bits, this coordinate at some places it could preserve monotonicity, and at some places it would violate monotonicity. So it has this mixed nature. On the other hand, now you get rid of this mixed nature, right? You split one coordinate into two coordinates, where one coordinate became purely monotone, the other one became purely anti-monotone. Okay? So it makes it makes a mixed coordinate into two pure coordinates, and now you can apply. You can start with the function f. You can apply the split operator on all the coordinates one by one, 1 through n. You are going to get a function g, which will, as Avi pointed out, this will be a function on double the coordinates. The function will be now it's a function of double the coordinates, right? And the coordinates are paired. Each coordinate, let's say coordinate number 1, it got split into a so-called plus coordinate and a minus coordinate, meaning monotone and anti-monotone. And then x2, this got into 2 plus and 2 minus, and so on, right? X n plus, x n minus. Okay? With the property that the function is monotone and all the plus coordinates, and it's anti-monotone on all the minus coordinates. And this is the sense in which the function is simple. Okay? And for simple functions, the Talleyrand, whatever inequality we are trying to prove, is true by the original version of Talleyrand. Okay? Right, so that's one thing. Yeah, and maybe finally I will say. Yeah. In the split, the number of sensitive edges, everything can only go down. Yeah, that was one property which was needed, right? Yeah. That right, this can only go down. Yeah. So the influences can only go down, despite the fact that you are doubling the number of coordinates. Yeah. Yes. The total influence is a total, right? So you are right that even in spite of doubling the number of coordinates, the sum still goes down. Okay, so finally, here is one precise manner in which G is actually morally f applied to random half of the coordinates. So G is a function from 0, 1 to the 2n to 0, 1, and here is a fact that this is a cube of 2 to the 2n points. It's possible to partition this into 2 to the n cubes of size 2 to the n each, right? Now, each of these cubes you could index by a subset of 1 through n, and then on that cube, if you take the restriction of G to that cube, it will exactly equal as if you had applied to the function f the switches in that set. So this is a formal sense in which G is really f applied to half of the coordinates. Yeah, and that's at least all I plan to say. And of course, as Avi pointed out, these operators are they are non-commutative in the sense that the order in which you do matters. So you have to take average over all random orders of doing everything.